class of tools to put them together into a device that you can sell to the consumer. Maybe CO detector, for example, is a nano tool. Not just like Johnson and Johnson who are selling cosmetic, which is also nano because there's a lot of zinc oxide and nanoparticle inside, cosmetic or as a commodity item, right? Essentially, that's a commodity item. But you can sell you can make more cash if you put them into a little device. So a lot of people, particularly in the electrical engineering folks, are working very hard on integrating this nano object into the device. Lastly, as well, we talk about these two graphs, and I just want to repeat a little bit. So we have usually when you're talking about charge particle, in this case electron, the sharp peak that you see is the elastic peak. There's no loss of the electron energy. And then at the very close to the elastic peak, you have vibrational energy loss. So the incident electron suffer an energy loss, and that loss is transferred into the material and excite the vibrational state of the material. So you have vibrational excitation of the material, which account for these little peak very close to, usually within 1 electron volt of the elastic peak. And then as you go further out, you have excitation. So electron excitation, moving the electron within your material to empty state, right, to empty orbitals in your material. So you can either move core electron deep in very close to the nuclei, or you can move valence electron into this empty state. Of course, the empty state in the jargon of the electronic engineer is conduction band, right? So we and the valence electron are valence band in material. So you are really making valence band to conduction band transition. You can of course move higher than conduction band, and this will give rise to little peaks further away from the elastic peak. So all these correspond, if you like, to electronic excitation and emission of electron in this regime. As you go further down, as you are measuring electron, slower and slower electron that reflected from the surface after your electron impact. And as you go very, very slow, if you try to detect the electron, usually below 50 or below 20 electron volt, you have a huge jumps of these drop or peaks, and they are usually featureless. They do not depend on the type of material that you have. So whereas this location of these peaks would depend on the material that you have. So gold would have a different peak location compared to silver, for example. But if you look at gold and silver, the secondary electron peak are usually the same. They are featureless. They are just a drop of electron emitting very close to the surface within 2 nanometer, 2 to 10 nanometer, if you like, from your surface. So they are really very nice if you can detect this secondary electron. Because they are refracting what's on your surface, the contour of your surface, and this is really what electron microscopy is all about. As we'll see a little bit later on, if you can detect this secondary electron, you can see the morphology of the surface structure, if you like, of your surface, because these electrons emit from near the surface. And then we talk about the mean free path of the electrons, and this is a so-called universal inelastic mean free path. And the thing to remember is around 50 volt, 50 to 70 electron volt, if you like, you have the shortest mean free path, 1 to 2 monolayer, if you like, 1 to 2 monolayer, about in terms of shortest mean free path that you need. And why you need this, why you need to know this is because if you send an electron beam about 50 or 70 electron volt, that means that you would get the most surface sensitivity because any electron come out will be coming out from 1 to 2 monolayer deep from your surface, right? If you use high electron beam, then the electron could come out from lower, deeper from the surface. So in order to optimize, to get the most surface sensitivity, you should use 50 to 70 electron volt to get the most surface sensitivity. Anything else, you would have not as sensitive because these are higher mean field path. And we talk about the reason why they all is universal is because of interesting physics, because most of the material have a very similar conduction band structure. So a lot of these scattering on solid are really due to electron scattering from your conduction band, and the conduction band of most material have very similar structure. So therefore, you have this universality that you see on here. Down here, you also have universality because the surface atom vibrate, so-called phonon vibration, which is basically if you have a layer, a grid of atoms, if you like, on a mesh, and you sort of shake this mesh, and the mesh will go up and down, and individual atom on the mesh will go up and down. So this sort of collective motion of your surface layer is known as phonon. It's known as surface phonon. So it's essentially surface vibration. And so these part is correspond to excitation, interaction of your electron wave with this phonon excitation, because when you go up and down, this surface vibration of course change the electric field or the dipole field of your surface, and they would interact with the electric field of the electron. And so what you see, these are due to phonon scattering, and they all look very similar for most material, and that's why you see this so-called universal inelastic mean field path curves. Okay, so we were there last day, and so we were looking at as an aside, why we need to use a vacuum, and in most cases something called ultra high vacuum, UX3. Why is UX3 necessary in order to study these services? I'm going to do two things. So it is necessary because a lot of the property, the technique used to probe these properties involve charged particle. Okay, so we have to send a probe particle into the surface and then look at what happened to the surface. So the surface could, the probe particle could refract back, or this probe particle could initiate stuff that come off from your surface. So you have to measure stuff that come off. Okay, so this technique involves free particle, such as electron and ion. And this free particle, of course, you can manipulate, right? So you should be able to control the velocity and how much you have and how tight the beam you have in terms of these charged particle beam. And then you watch what happens when you bash this beam onto the surface, onto the material that you have. Does it change the energy of this charged particle beam? Does it initiate other stuff like cause the material to emit photon or emit other electron that you can detect? So you initiate stuff using this probe beam, and because you're dealing with this charged particle, they don't travel very far. The charged particle doesn't travel very far in air because it will collide with an air particle very quickly and then get absorbed. And then the trajectory, the kinematics, if you like, of these charged particles will change due to the collision. So what you want to do is that you want to keep these charged particles in vacuum, inside vacuum, so that you have less chance of these charged particles scattering off something that you don't want before it hit the surface. Okay, so that's the reason And most of the time, you involve a web key